All right, as promised, here are the solutions to the extra credit assignment. So here's the figure for the first problem. So I'll start by drawing a free body diagram for the left mass. There are two forces acting on it. There's gravity acting down, that's M1G. There's a tension in the rope acting up. I'll call that T1. And the mass on the right, which is of course bigger, it has to have a larger force vector from gravity, that's M2G, and the tension pulling up, which we'll call T2, is there. Now, since you know the system moves this way, if that's the acceleration of the rightmost mass, then the leftmost mass is forced to go up with the same acceleration. So T1 must be bigger than M1G, and M2G must be bigger than T2. So from those two, we write down the equations of motion that govern those two masses moving in linear motion. And I think you can see that there'll be T1 minus M1G on the left, equaling its mass, M1A. And on the right, it must be that M2G must be bigger than T2, and that will equal the mass of the second one times its acceleration, and both of those accelerations are equal because they're linked by a string that can't stretch. So there's the first two of our equations. Now we need two more dealing with the pulley. Okay, as promised, here are the solutions to the extra credit problems. The first problem has two masses connected by a string which cannot flex. The string passes over two frictionless bearing pulleys. Each pulley has the same mass, but the one on the left is a sphere and the one on the right is a disk. They both have the same radius. So we're going to get, in order to solve this system and find the acceleration of the system and find the tensions, we're going to have to write down two equations using F equals ma for the two masses M1 and M2 moving in linear motion, and two equations, one for each pulley, for Newton's law for rotation, and that would be the sum of the torques as I alpha. So we'll start with the linearly moving masses. I'll draw a free body diagram in place, so it's technically not a free body diagram. M1 feels the force of gravity, M1G acting down, and it feels a slightly larger tension in order for it to go upward. We'll call that T1. M2 feels a bigger force down, and that is M2G, and acting upward, opposing that but not winning, is tension T2. So mass on the left goes upward. It has an acceleration up. I will choose positive direction upward for that one. The one on the right accelerates down, so I will choose positive down. They both have the same acceleration a in their respective directions. So I get two equations. At the top of the board, on the right here, I will write down the equations for the left mass first. And I think you can see that's T1 minus M1G is M1A. And the mass on the right, M2G, is bigger than T2, so it's M2G minus T2 equals M2A. And I shouldn't say it's M2G minus T2 because M2 is bigger. It's because I chose positive X to be down. And it's because I chose this direction here that it's M2G minus T2. Okay, so now we have two equations right there. And you might think from that we could solve the whole problem. But the reason we can't, of course, is because the tensions in the first and the second equation here, T1 and T2, are not the same. Okay, so now what we have to do is write down Newton's second law for each of the pulleys. So let's look at the pulley on the left. There is a tension in the string going downward. That's T1 again. There's a tension pulling to the right, slightly bigger than T1. I'll call that T prime. And on the pulley over here, there is a tension T prime pulling this way. And on this side of the pulley, there is a tension T2 acting downward. All right, so to calculate torque, we do R cross F. Remember that torque, the magnitude of the torque, is R times F times the sine of the angle theta. But in this case, the angle theta is 90 degrees because the radius vector from here to there meets this tension at a 90-degree angle, and the radius vector from here to here meets this tension at a right angle, and likewise for the other pulley. So I think you can see then that I will have, for the leftmost pulley, I will have, the pulley rotates this way, right? So the torque due to T prime is going to beat the torque due to T1 that's opposing it. So I'll have T prime minus, actually I'll have T prime times R, but I'll also have a minus T1 times R, so I will factor out that R from both of them, and then that's equal to the moment of inertia of the pulley on the left. I'm going to call that I sub A, and times alpha. Likewise for the pulley on the right, its angular acceleration alpha is that way, and T2 is obviously bigger than T prime, so it must be, oops, I just realized that up here I wrote this as T1, and it shouldn't be T1, it should be T prime. Sorry about that. All right, so back over here, the torque now for the rightmost pulley will be T2 minus T prime, all times R, is IB times alpha. Okay? So this pulley on the right has moment of inertia IB, the one on the left, moment of inertia IA. And we know what those are. The sphere about its center of mass has a moment of inertia of 2/5 mr squared. And a disk has a moment of inertia of 1/2 mr squared. Both of those pulleys have the same mass m and the same radius r, so that will simplify things in the problem. Okay, so now we look at these four equations, and we see we have how many unknowns? T1, T2, A, and alpha. And anything else? Oh yes, and then we also have T prime. So we have 5 unknowns and 4 equations. That's not sufficient to solve the problem. We need one more equation, and that equation is the connection between alpha and the linear acceleration, and that comes from assuming that the string doesn't slip on the pulley, and the rolling without slipping constraint tells us that A must be R times alpha, and it's the same constraint for both pulleys because both pulleys have the same radius. If they didn't have the same radius, then you would have A equals, R1 times alpha 1, and A equals R2 times alpha 2, and you'd have different angular accelerations for the two pulleys. Okay, so now I'm going to use this equation to eliminate the alpha in each of the above two equations, and now I'll replace it with A over R. All right, so now I'm going to rewrite those 4 equations, and when I do, I'm going to take these bottom 2 equations here, and I'm going to also divide each of those bottom 2 equations by R. When I replace alpha here with A over R, and then I divide by R here, then I will get an IB over R squared in the bottom term and an IA over R squared in the third equation. So here are the resulting 4 equations rewritten. So I'll rewrite those here. And first 2 are unchanged. Oops. And now I rewrite the last 2. Okay, now all I have to do is add up each of the left-hand sides of these four equations, and then I add up each of the terms on the right-hand side. So on the left-hand side, notice what happens, that when I add these up, T1 will cancel with minus T1, and T2 down here will cancel with minus T2 over here. And likewise, T prime here will cancel with minus T prime here. So the only thing I'm left with when I do this problem is M2G minus M1G, and on the right hand side, notice that IA over R squared, I look at this equation here, and you can see that IA divided by R squared is just 2/5 M. Likewise, IB over R squared, looking at this equation, is just IB over R squared is just 1/2 M. Okay, so when I add up all the terms on the right hand side, I factor out an overall term A, and I'm left with the following: M1 plus M2, the sum of the linear masses, plus two more terms. I get a 2/5 M, that's for the left pulley, and I get a 1/2 M from the right pulley, and all of that is times A. Okay, so now I've rewritten that equation at the top, and notice that I have simplified it a little bit. I've taken the 2/5 M and the 1/2 M and added them together. That gives 9/10 M. And now I can solve this for A. The acceleration for the system is just this term M2 minus M1. That's the difference, that's the net gravitational force making the whole system move. It's the difference in the pull of gravity on those two hanging masses. And then downstairs, we have essentially the effective mass of the system, which is the sum of the two linearly moving masses, plus an effective mass due to the rotational inertia of the two pulleys. And in terms of the mass, little m for each pulley, that's how that term ends up contributing. So here is an expression for the acceleration of the system. That's the first part, is to get that acceleration. Okay, now the next thing I asked for was the tension T prime between the two pulleys. You can get that tension T prime either by working on the left mass and moving upward, or working with the right mass and moving your way upward till you get to the middle of the pulley. So I'm going to work with the leftmost mass. And in the leftmost mass, we know that T1 minus M1G is M1 times A. Now we know what A is. It's this messy box here. So if you put that in right here for A, and then you add M1G to both sides, you'll get the tension T1. So I would just take M1. In fact, if you notice, there's an M1. This is M1G, and this was M1A. So when I bring this term to the other side, it becomes plus M1G. And there's also an M1 on the right-hand side. So if I factor out an M1, I end up with A plus G. So here is an expression that would allow you to calculate the tension T1. All you have to do is take this horrendously complicated fraction in here, plug it in here for A, add G to that, and multiply the whole thing by M1. So we could write that out, but that's essentially good enough. Once we've got T1, we can work our way back up to the equation for the pulley on the left, and that was T prime times R minus T1 times R is IA times alpha, but remember alpha was A over R. Alright, so now I solve this for T prime. I factor out an R from both sides, and I think you can see that if you do a little algebra, maybe stop the video here and solve it yourself. Go ahead, do it. solve it. Just pause this and then figure it out, come back. All right, hopefully you've solved it, and you should get the following. On the right-hand side, you will get a T1 plus IA over R squared times A. And that is good enough in my mind, because now once you've calculated T1 in the box here, you take that value for T1 and you put it right in here. It's going to be a horrendous mess. And then you add it to IA over R squared times A. That's this box being substituted again down here. And that'll be your answer. It's a total mess, but there's not too much utility in writing it all out except just for the fun of it. I know that's kind of sick. All right, there you go. That's that solution.